Welcome once again in the class of design of steel structure. So we are learning the plastic analysis. Uh, I am Mr. S. Sugla, Assistant Professor, Civil Engineering Department. Now the plastic collapse. The plastic collapse of a structure depends on the redundancy. When sufficient number of plastic hinges are formed to convert the structure into the mechanism, the structure will collapse. At such stage, deflection increase very fast at a constant load. The collapse of the structure can be partial or completely or over complete. So number of plastic hinges developed, that is N, and collapse mechanism. So number of plastic hinges are less than R plus 1, that is partial collapse. Number of plastic hinges equals to R plus 1, that is complete collapse, and number of hinges greater than R plus 1, that is over complete collapse. So this is the plastic collapse. Now the classification of the section. So this is the new concept introduced in IS 800 2007. The member strength is evaluated when the stresses are reached to yield stress. The cross section of the member is to be proportioned in such a way that local or overall buckling of the elements of the cross section, such as flange or wave, does not occur before the limit state of the strength is achieved. So plate elements of the cross section may buckle locally due to compressive stress. The local buckling can be avoided before the limit is achieved by the limiting the width to thickness ratio of the each element of a cross section subjected to a compressive compression due to axial load, moment, or shear. On the basis of this, the four classes are defined as follows in the IS code. So here you can see in this clause number 3.7. So it has been divided into the following classes, that is class 1 plastic, class 2 class 2 is compact, class 3 is semi compact, and class 4 is slender. So as you can read over here, in class 1 the cross sections which can develop plastic hinges and have the rotation capacity required for the failure of the structure by formation of the plastic mechanism, the width to thickness ratio of the plate elements shall be less than specific under the class 1 in table 2. In class 2, the cross sections which can develop plastic movement of resistance but have inadequate plastic hinge rotation capacity for the formation of the plastic mechanism due to local buckling. The width to thickness ratio again has been mentioned in the uh, in this table number 2. In class 3, again the cross section in which the extreme fibers in compression can reach yield stress but cannot develop the plastic movement of resistance due to local buckling. So width to thickness ratio of the plate elements shall be less than as specified under this class 3 in table 2. In class 4, the cross section in which the element buckle locally even before the reaching at the yield stress, the width to thickness ratio of the plate element shall be greater than the specified under class 3 in table number 2. In such cases, the effective sections for design shall be calculated either following provisions of IS 800 to account the post local buckling strength or by deducting the width in the compression plate element in access to the semi compact section limits. So here you can see this is table number 2. So this B by TF ratio has been given over here. And these are the different classes where the strain has been mentioned. Now, the ideal section, that is class 1, it produces the uniform stress Fy in both the bending and compression and bending tension. The moment of resistance due to this stress distribution is Mp. The yielding of the section is no longer resist further load. Two parts of the member on either side of this section rotates about the neutral axis of the yielded section and collapse occurs. A compact section develops a plastic moment of resistance. So here you can see this is the ideal section, that is for the class 1. You can see it is completely stressed. The compact section develops the plastic movement of resistance, but because of the local buckling, it has an inadequate rotation capacity. A semi-compact section is not able to develop a plastic movement of resistance. So here you can see this is the compact section, which is having less than this. This is the semi-compact section. So it is not able to develop a plastic movement of resistance. Extreme stresses can be reached up to Fy, but local section is not yielded fully due to the local buckling. And last is the slender section, as you can see over here. It is not able to develop even a yield stress at extreme fiber because of the local buckling. Such section should be avoided. So this is the plastic movement. So in this, it Fy reaches to plastic. This is a kind of reaching at the fully yield, but it cannot develop the plastic movement. It deforms before the plastic movement, and this semi-compact is fail at the yield, and this slender is failed before the yielding. Now, in exam, the question will be asked sometimes that classify the following sections in the different categories which are given in the code. So we'll take some sections and check whether in which category they are falling. So first, that is ISLB 300. So breadth is the 150 mm, thickness of the flange is 9.4, H1, that is clear depth of the web, is 245.1 mm, thickness of the web, that is 6.7 mm. So first we have the formula for the stress, that is 250 divided by Fy, under root 250 divided by Fy equals to 1. So B by 2, because this Fy equals to 250, so it is 1. And this B by 2 by TF ratio, that is 75.9, 75 divided by 9.4, that is 7.9, which is lesser than 9.4 E. Again, which is given in this table. You have to check these conditions. Then this H1 divided by TW, that is this depth divided by this, that is 36.58, which is less than 84. So 84 into strain. So we need to check these two conditions, that is in this table, that is in the code. So basically we are evaluating this ISLB. So web of the eye. So D by TW ratio should be somewhere over here. So it is this lesser than 84 into stress. So web is plastic, and about the web of the or the outstanding leg of the particular angle member, or we'll consider it as angle member. So it is lesser than 9.4. So obviously it is also, flange is also plastic. So full section is plastic. Now we'll consider ISHB 400. So B is 250 mm, BF is 12.7 mm, TW is 9 mm, and H1 has been given 340 mm. So again we need to check this B by 2 and TF. So by checking this, it is 9.84. So which is again greater than this, lesser than this 10.5, greater than 9.4 plus less than 10.5. So this flange is compact, and this H1 by TW ratio, that is 37.37, which is lesser than this 84 into stress. So sorry, strain. So web is plastic. So section is the compact. Now ISFG 200. The width is 200 mm. The thickness of the flange is 9 mm. H1, that is thickness or height of the web without considering the flanges, and the thickness of the web is 6.1 mm. So this ratio is again 11.11, which is greater than 10.5 but lesser than 15.7. So it is falling in between. So it is semi-compact. Flange is semi-compact, and this H1 by TW ratio, that is 25.96, which is lesser than 84 into strength. So wave is plastic. So section is the semi-compact section. And for this ISA 100 by 6, grocery has been given. B is 100, D is 100, and T is 6. So B by D ratio is 100 by 6 and D by D is 100 by 6, which is 16.66 and 16.66, which is greater than 15.7. So in case of angles, here you can see both the ratios are greater than this 15.7, and third condition is B plus T divided by T, this one, this condition, which is 33.33, which is greater than 25 into strength. So obviously the section is slender. So this is all about how to classify the sections. This is all for today's lecture. Thank you.